In this video, we'll discuss Newton's law of gravitation and how to calculate the size of gravitational force between two masses. Newton spent much time studying data collected from the astronomers who preceded him. Between that and an apple hitting him on the head, as the rumour goes, he came to a simple but influential conclusion. Now known as Newton's law of universal gravitation, it's a simple formula that has taken astronauts to the moon and back. Newton's law of gravitation says that every object in the universe, whether a planet, a person, or a pencil, attracts every other object. The force between them is 1. Proportional to the product of their masses, meaning that the force between heavier objects is greater, and 2. Inversely proportional to the square of the distance between their centres, meaning that the further apart the objects, the weaker the force. To put a value on the strengths of the force between any two objects, we can use this equation. F equals G times the product of m1 and m2 over d squared. m1 and m2 are the masses of the two objects, and d is the distance between their centres. The big G is the universal gravitational constant, which equals 6.67 times 10 to the minus 11 cubic meters per kilogram second squared. As with any force, the units of gravitational force is newtons, commonly represented by a capital N. Newton's law of gravitation explains why we stay planted on the Earth and why planets orbit the Sun. This gravitational force provides the necessary centripetal force. Even though gravity exists between all objects with mass, it's more noticeable when at least one has a large mass. Now for a worked example. A 500 kilogram satellite orbits Earth at an altitude of 500 kilometers. The mass of the Earth is approximately 5.972 times 10 to the 24 kilograms, and the gravitational constant G is approximately 6.674 times 10 to the minus 11 Newton meters square per kilogram square. To calculate the force, we first need to know the centre-to-centre distance between the two masses. That is, the altitude plus the radius of the Earth. Adding these tells us that the distance is 6,008,071 meters. Plug all the values into the force equation and we see that the gravitational force on the satellite by Earth is approximately 4,221 newtons. Anytime you use this equation, make sure that you give the distance between the centre of the two masses, not the distance between their surfaces. Distance is always measured in meters, and masses are measured in kilograms. We've covered Newton's law of gravitation and how to use it to calculate the gravitational force between any two objects. Why not try some practice equations? If you found this video helpful, subscribe for more like it.